So here we are in my kitchen. I'm gonna make some tea. I'm gonna make organic black chai. And I have two different straws that I can put in my tea. This one is made of metal, and this one's made of plastic. That tea must be ready. Okie dokie. So I'm going to put the plastic straw in my boiling hot water and my metal straw in my water. I'm going to wait for my tea to steep. Okay, I'm going to touch each one of these with my hands. What will be the difference in the way they feel? What is this concept? This concept is thermal conductivity, the way the heat moves through the object based on the material of the object. Let me show you more. Thermal conduction is the way heat will move through a substance. So you might recognize that this happens, like in the example with the different material straws or spoons, or when you walk into the bathroom and touch the toilet seat, or your feet touch the tile floor after coming from the carpet floor. Even though the carpeted floor room and the bathroom are probably at the same temperature, the tile feels colder than your carpeted room. Well, you are at a higher temperature than the tile in your bathroom. So heat will transfer from you to the tiles in the bathroom. The rate at which this happens is heat conduction. If this happens at a meaningful rate, then you'll feel a kind of delta T of your body temperature. So objects with a higher rate of heat conduction will feel to you colder than objects with a low rate of heat conduction. So looking at this in the straw, you might have a rate of heat conduction in the metal straw that's quite visible. You can see the heat traveling up the straw at a pretty high heat-like velocity, length per second. But the heat in the plastic will be transferred very slowly. Let's look at the parts of this equation that will tell us about this heat motion. So here's our thermal conduction equation. QT equals kappa A delta T over D. So this is your rate of heat exchange. So it's the heat, Q is heat, over some unit of time. Heat, remember, is an energy required to get some sort of substance to a certain temperature. So this is in joules, and time is in seconds. So over here you have joules per second. What is that? I know you see what I did there. So on this side you kind of have watts, right? Joules per second. On our other side, we have kappa, area, delta T, and D. So kappa, K, is a constant depending on the material that we're working with. So it will be different for, say, the tile in your bathroom and the carpet on your floor. A is for area. Area of what? Area in which the heat will be able to move from one thing to another. So the section of tile floor that is in contact with your foot, for example, the area that is experiencing the delta T. This is a temperature difference from one surface to another. Then D is the distance across the material that the heat has moved, or the length. So looking at this picture here, if you have hot tea, and then you have your straw, like this, then it will have a cross-sectional area where heat can move. I guess our area would be kind of more like a toilet paper roll. And you then have the distance in which the heat will travel up the straw, D. Good? And notice heat always moves from hotter to colder regions. So let's practice applying this equation of thermal conduction to some problems below. The answers are listed in each one of these problems, and I will help you if you want to continue watching. If not, just go ahead and pause. Okie dokie. So for this one here, we want to know how many joules of heat are transferred in 1 hour. Let's deal with the hour first. So what time are we dealing with? 1 hour. Do we use an hour? No, we use seconds. So an hour is 60 minutes, and each minute has 60 seconds in it. So replace T with 60 times 60. Let's see, the delta T on this side is a change in temperature. So we can write out our change in temperature between our two surfaces because we know that the outside is 5 and the inside is 20. So our delta T is 15. Now, the kappa value comes from what substance we're looking at. So that information is going to be over here. Thermal conduction constant. We have the area. This is the area between the two different temperatures. So that's going to be the area of our window right here. So we'll have 0.65 times 1.25. And then you'll have your distance, the last piece, a thickness of 2 centimeters, but watch your units, please. So here you have 0.02. From there you can solve for Q and you get the answer listed. Nice job. Okay, so you've read this problem. So this is 350 K. Base is going to be held constant at 250 degrees Kelvin. We want to know what's the thermal conductivity of the rod. So let's write down our thermal conductivity equation. So Q over T equals K A delta temperature over D. Now our graph has Q as a function of time. So let's go ahead and isolate Q over here and multiply by T. Okay, so we can get it to match up with what our graph equation is. Now let's write our equation for our graph. So our graph says Q is linear with respect to time. So let's just go ahead and find the slope to fill in there. So we have a rise over run. Let's use these 2 points. Rise 10, run 4. So our slope is 10/4. So here's our equation for Q using our graph. Here's our equation for Q. Knowing the equation for Q, let's map them together. So right now it says that the information 10/4 equals all this stuff right here. So we can go ahead and fill out 10/4 equals kappa, which is what we want to know. Area. Do we know the area of this straw? 1 meter long, 2 centimeters in diameter. So pi, now diameter, change that to radius, pi r squared. That gives us our area. Our delta T comes between our two containers, 350 and 250, so 100. And then we have our distance, 1 meter. That allows us to solve for kappa. Top red bar has a 200 watts per meter Kelvin thermal conductivity, while the bottom blue bar has a thermal conductivity of 400 watts per meter Kelvin. So our delta T between the two plates is 100. We know the direction of heat flow. Heat will be flowing this way, Q, from hotter to colder. And in which bar will the heat be able to travel faster? Well, larger the K, right? Faster the motion. How much faster? Our equation, Q, T equals kappa area delta T over D. So it says that the net energy transferred through the bar in a given time is Q. What's the net energy transferred through the bottom bar during the same time interval? So the time intervals for each bar is the same. The distance for each bar is the same. The delta T for each bar is the same, and the area for the bar is the same. So that means that kappa and Q are directly related. So if kappa doubles, then the amount of heat will also double. And there we get our answer, 2Q. Something cool to notice is that if you rearrange this equation, then you can have, divide the Q out to the other side, you can have kappa A delta T over D equals Q over T time. Moving the Q over to the right here, and the D up here gives us a velocity for which the heat will move.